Connective tissue is one of the 4 basic tissues. It can be divided into general connective tissues and specialized connective tissues. We'll look at the general connective tissues in this series of videos, and we'll look at the specialized connective tissues later on in the year. These are the learning objectives which you should use when studying this material. The characteristics of connective tissue are diametrically opposed to the first tissue that we looked at in detail, epithelial tissue. In connective tissue, the cells are separated and surrounded by a large amount of extracellular matrix materials, whereas we saw in epithelial cells that those cells were very tightly adhered to one another and had very little separation between them, and therefore very little extracellular matrix. In fact, in connective tissue, there's a predominance of matrix over cells. The cells can be put into 2 basic categories: resident cells, which essentially are born, function, and die, and then are replaced within the tissue compartments. Those are the resident cells, which are responsible for producing and maintaining the components of the extracellular matrix. And the second group is the wandering cells, which are predominantly differentiated in the bone marrow, and by way of the blood vasculature enter into the connective tissue compartments, where they move around through the matrix and perform their various functions. A third characteristic of connective tissue is that it's well vascularized. This contrasts with epithelial tissue, which was avascular. Connective tissue is generally located between, around, and underlying the other basic tissues. Recall that epithelial sheets are always underlined by a basal lamina and usually a connective tissue compartment underneath them, which provides them with their metabolites. Some good examples of this are the dermis of the skin and the GI tract and the organ capsules. Connective tissues are derived predominantly from the mesoderm and are categorized generally by the morphology and arrangement of their cells and matrix components. This diagram shows a generalized connective tissue compartment. You can see that at the top of the diagram you can see the epithelial sheet, which is resting on a basal lamina, as we discussed. And then underneath that is that connective tissue. There are scattered various types of cells that live there, and we will discuss each one of those, as well as all the matrix components, which can be divided into fibrillar and non-fibrillar components. So what does connective tissue do? Well, the functions of connective tissue are first to provide a supportive framework or filler for other tissues and organs in the body. It functions also as the media in which transport of nutrients and wastes occurs, that is, between the blood and the cells. It is the place where metabolites are stored, most particularly in fat cells, which we'll take a look at in a few minutes. It is the environment in which defensive responses occur. So the immune response and inflammatory reactions take place in connective tissue compartments. And the matrix components are the basis, and the cells are the basis for which tissue repair following injury occurs. So as I said before, there are 2 basic categories of connective tissue cells. You can see in blue are the ones we're going to look at in detail. There are other cells, of course, that are found in these connective tissue compartments, which will be discussed in detail at other times. So first, let's look at these resident cells. The first cell I want to talk about are the fibroblasts. Fibroblasts are generally large cells with a lot of synthetic capacity. Morphologically, they have typically a large oval pale staining nucleus, that means it's euchromatic, actively transcribing, and an abundant RER in the cytoplasm, which means it's just a reflection of their synthetic capacity. They make and export all of the extracellular matrix components, both fibrillar and non-fibrillar ground substance. When they're in the inactive phase, they might be called a fibrocyte. You might see that in the literature. The top image here shows the active fibroblasts with their very plump cytoplasm and very euchromatic nuclei. You can see that they also have cytoplasmic extensions out into the matrix. That feature is present even in inactive fibroblasts with those long extended cytoplasmic processes. However, the nuclei are quite condensed, dark, and heterochromatic because they're not really actively transcribing at this point. And you can see that the cytoplasm is not so abundant, and therefore the cells are not quite as plump. They're quite flat looking in the inactive phase. And that's just a reflection of their lack of synthetic capacity when they're in their resting phases. The second resident cell is called the adipose cell, or the fat cell. This comes in two types, unilocular or white fat, and multilocular or brown fat. Unilocular is actually quite abundant. It has a white appearance grossly in unfixed tissue. This is characterized by each cell having one very large lipid droplet which takes up the majority of the volume of the cytoplasm. Therefore, all of the cytoplasm and the nucleus are pushed to the periphery of this cell. These, of course, are specialized for storage of triglycerides as an energy source. Now, multilocular fat, or brown fat, appears a little bit browner for two reasons when it's seen in gross unfixed specimens. And that's because it has a larger amount of mitochondria within each cell, and it also has a larger amount of vascularization throughout the tissue. These cells are somewhat smaller than white fat cells, and each one has numerous small lipid droplets in the cytoplasm. And these cells are specialized for heat production, which is something you might have inferred from the large number of mitochondria in their cytoplasm. So adipose cells have a lot of different functions other than as the concentrated energy storage medium. They also act as thermal insulation, for instance in the hypodermis of the skin, which is a layer of fat cells directly underneath the epidermis and dermis. They also act as shock absorption and cushioning, where they are situated around organs such as the eye and the heart, and in the palms and soles. Another function is that adipose tissue acts as a space-filling media between other tissues and organs. And finally, adipose tissue has an important endocrine function, producing a number of hormones and cytokines. Now, I'm just going to talk about two of the hormones that are made by adipose cells, or adipocytes, and those are leptin and adiponectin. Leptin acts to inhibit appetite and stimulate the metabolic rate. This opposes the action of ghrelin, another hormone, which is made in the GI tract, which actually stimulates the appetite. The other hormone made by adipocytes is adiponectin, which helps to regulate glucose levels. Here are a couple of examples of histological sections of unilocular or white fat. So on the left you see the low magnification picture, and the cells really look like just empty space. When you look at the cells themselves at higher magnification, as on the panel on the right, you can see that the cytoplasm is just this thin rim, and most of the volume is in fact that lipid droplet, and the nuclei are pushed to the edge, and that's why they're called sometimes the signet ring appearance of the fat cells. This is different than multilocular or brown fat. I've outlined a single brown fat cell here, and you can see the numerous lipid droplets and the peripheral nuclei again in these cells.